Hello, my name is Miguel Delgado, and I'm a recent PhD from the University of Illinois in Urbana-Champaign. I'll be starting as a McWilliams Fellow this fall at Carnegie Mellon. And for this symposium, I'll be presenting on supermassive black hole binary candidates, combining light curve data from the Dark Energy Survey and the Sloan Digital Sky Survey. And this is work done with the Illinois Quasar Group, who have led much of the light curve data analysis. And here I'll be presenting on that, as well as the gravitational wave interpretations that come with supermassive black hole binary candidates. So one of the various one of the sources that Lisa hopes to detect are merging supermassive black hole binaries, albeit a little bit less massive than the typical supermassive black holes. And there have been a number of supermassive black hole binaries that have been found in the electromagnetic window, spanning a variety of orbital separation scales. So from the tens of kiloparsec separations is where direct imaging of dual AGN is possible. Going down to the kiloparsec scales is where double peaked narrow lines might be seen in the spectra. And going even further down in separations down to the tens of parsecs is where very long baseline interferometry from the radio might be able to resolve double radio cores. Now, overcoming the final parsec problem is still a theoretical uncertainty, but there have been a number of candidates that have been found at the 0.1 implied at the 0.1 parsec separations. So using the radial velocity method to look at spectral variations that come from orbital velocity, from the orbital velocity, and then down at the tens of milliparsec separations is where light curve variability has been used to indicate whether or not quasars might show periodicity that might be indicative of binary motion. And there have been a number of candidates, so order hundreds, that have been found from time domain surveys at this milliparsec separation scale. And this is the scale where gravitational wave emission is dominating the orbital inspiral towards a merger. So the search for milliparsec supermassive black hole binaries continues in these periodically variable quasars. So how can we tell if these candidates are real or not? So it has been shown that if the baseline is less than 2 cycles, then red noise might masquerade as periodicity. So pulsar timing arrays have provided upper limits on the nanohertz stochastic gravitational wave background and have shown that not all candidates can be real. And if they were, it would produce a gravitational wave background that would be in tension with the pulsar timing array upper limits. So one would need to observe longer in order to see if such periodicity persists. And on the red noise side, going back to that point, on the right here is light curve data from PG 1302. So the blue and black data are the light curve data for the V band magnitude, and the transparent red model is a red noise model, and the solid red opaque line is a periodic model corresponding to the binary hypothesis. So these two models are indistinguishable given the length of the data set. So what these authors, Vaughn and others at 2016 have found is that observing about greater than 5 cycles might be needed in order to rule out false positives that come from red noise possibly being indistinguishable from true periodicity. So here, presenting our main result, we find 5 new supermassive black hole binary candidates by combining SDSS and DES multiband light curve data. So the parent sample here is about 650 quasars with sufficient epochs. So about 30 epochs in SDSS and about 50 epochs in DES. And to select these periodic quasars, we use the generalized Lomskarville periodogram and compare the light curve data with damped random walk models. And for interpreting our catalog of periodic candidates, we fit periodic burst accretion models that are informed by viscous hydrodynamic simulations. And we also test the Doppler-boost hypothesis. So our study spans an observing baseline of 20 years. That's by it being able to combine both DES and SDSS. And so this 20-year baseline is much longer compared to the previous studies. So Catalina Real-Time Transient Survey, the Palomar Transient Factory Survey, and PanSTARRS. Our data are at similar cadences to those previous studies. And also, we are using multi-band light curve data in the G, R, I, and Z bands. So from our methods, the number of candidates that report is 5 with the baseline of 20 years. So I won't have enough time to go through all the candidates, but I'll be presenting our best one so far, which is JO252. So on the right plot here is the light curve data in the G, R, I, and Z bands. And the mass for this particular quasar is about 10 to the 8.4. It's at a fairly high redshift of 1.5, and the observed period here is about 4 years. So for the circumbinary disk light curve model, so mapping the accretion rate to luminosity from one of the previous models coming from Ferris et al. In 2014. The applied mass ratio for this kind of periodicity is corresponding to about a mass ratio of 0.1. So if JO252 is indeed a binary, then the coalescence timescale would be something about 10 to the 4 years for this type of system. And then we also compare to the relativistic Doppler-boost hypothesis. So variability coming from Doppler beaming along the line of sight, where for an accretion disk that's around the black hole that comes along the line of sight, it'll be brightened by the relative Doppler motion, and it will dim once the source moves away along the line of sight. So here we fit a broken power law model to JO252 spectrum. And with these power law fits, we can apply the Doppler boost hypothesis. So the relation here to first order in V over C, the relation of the amplitude of one light curve band to another band is equal to this fraction here, 3 minus alpha sub I over 3 minus alpha sub j. So this ratio of the amplitudes obeys this relation for ratio of the spectral indices from our broken power law fits. And the left-hand side of this equation is the y-axis on the right-hand plot, and the right-hand side of this equation is the x-axis of this right-hand plot here. So the black line is the Doppler-boost relation, so the equation that's shown on the left, and these different 6 here data points are the different band ratios here for the G, R, I, and Z bands. So what you can see here is that there are a handful of data points here that are in tension with the Doppler-boost relation. So this is telling us that circumbinary disk variability would be preferred over the relativistic Doppler-boost hypothesis. For the other 4 binary candidates, their masses range from about 10 to the 8 to 10 to the minus 10 to the 9, with similar observed periods, about 3 to 4 years. And also follow-up observations are with DECAM are underway to help extend the baseline and further test the binary hypothesis. And so when applying, again, the Doppler-boost hypothesis from the previous slide for each of these candidates, we are finding that the Doppler-boost hypothesis is not preferred as explaining the periodicity for these candidates. So this is consistent with a theoretical study by Kelly et al. In 2019, where they, from using cosmological simulations and using sensitivities from telescopes like the Catalina Real-Time Transient Survey and LSST, they claimed that observing periodicity from disk variability or hydrodynamic disk variability might be more common than Doppler boosting. So if these binary candidates are real, would LISA be able to detect their eventual mergers? So our best candidate, J0252, its eventual merger would certainly be detectable in the LISA band. So on the right here is an SNR contour plot over mass and redshift, with the y-axis being log 10 of the redshift and the x-axis being log 10 of the total mass. So these are the typical waterfall plots that are shown for futuristic detectors like LIGO, LISA, and SKA, for example. So the more transparent contours are for LISA and an SKA-like detector, and the opaque contours on the bottom right are for the nanograph 11-year sensitivity. And the contour colors, so SNRs ranging from 10 to 100 are in purple, 100 to 1,000 in light blue, and so on. So EM surveys can certainly find supermassive black hole binary candidates at redshifts beyond the PTA horizon, and that's certainly a complement for future transient surveys that'll take place. And there is some hope that LISA might be able to detect more massive supermassive black hole binary mergers at high redshift. And so, of course, the future of multi-messenger astrophysics with sub-parsec supermassive black hole binaries is both bright and loud. There are a lot of candidates that have been found so far from recent transient surveys. And also pulsar time Uri upper limits are already constraining supermassive black hole binary candidates. Next generation transient surveys will find even more candidates and follow up on current candidates. And another thing to look forward to, in addition to the upcoming LISA mission, is that pulsar time Uris will eventually detect the nanohertz gravitational-wave background in the coming years. Thank you.